Hi everyone, welcome to this channel. Today, we will be talking about the other explainable AI algorithm, namely GradCAM, and also some other variants like GradCAM++ and ScoreCAM. In order to dumb it down, we're going to cover the intuition, mathematics, as well as the code implementation of this technique. And please stay tuned to the end of this video. I also want to discuss the purpose of explainable AI and how it can help us. Alright, let's start with a quick recap of our previous topic, which is CAM. We're going to take VGG as an example to explain CAM, and this is how it works. VGG 16 is composed of 13 conv layers, 5 max pooling followed by 3 FC layers, which stands for fully connected layers. Therefore, the number of layers having trainable parameter is 16, 13 conv layers and 3 FC layers. So this is the reason why the model name is VGG 16. And VGG has the this kind of block structure, as you can see in this figure. Each block consists of a sequence of conv layers followed by max pooling. And after each pooling layer, the size of the feature map that flows into the block will be reduced by half, and the number of channels will be doubled. So after 1, 2, 3, 4, 5 conv blocks, we get the last feature map with the shape of 7 by 7 by 512. Then the three-dimensional feature map, the feature map matrix will be flattened to a 25,088 dimensional vector. After that, the vector goes through the three fully connected layers until we have the final layer, which is the classification result. So fundamentally, this is the overall architecture of the VGG 16. To make it work, we have to train the model by feeding one dataset to the model and start the training loop, like forward pass, loss calculation, back propagation, parameters update according to the gradients under a given optimized strategy, and so on and so forth, right? And we repeat the loop over and over again until we get a converged model with, let's say, maybe 90% of accuracy. So training is done and the model is ready to go. Now, suppose that we want to make the model explainable. This is where CAM comes in. First thing we need to do is to modify the model's architecture to make it work with CAM, considering that the very restrictive characteristic of CAM, starting by remove the head from the model and hook up a new gap plus one FC fully connected layer. So this modification forces us to retrain the model, and usually we only retrain the ways here that mapping the gap and the final classification result, and freeze all those weights or parameters of the backbone. And after few epoch of training, once the loss converged, we get the new model ready, which is explainable. Next up, we start to explain the model by feeding an input image, which is a tabby cat photo in this case. I believe it's a tabby cat. I'm not quite sure because I just randomly picked from the internet. So please correct me if I'm wrong, okay? So we fit this particular image into this model, and it goes over the conv blocks, then stops here where it becomes the feature map that we are interested in. And next, since we want to explain the model by figuring out how each pixel in the input image contributes towards the final result. Now, given that the highly semantic characteristic of this feature map layer, I think we can expect it as a representative of the original image. So once we figure out which areas in this feature map contributes the most to the final result by producing a sort of contribution distribution heat map, then we can map that heat map back to the original image to reflect the logically equivalent, right? And so the question here is, when it comes to the 512 layers of feature map, how do we get the weights representing the importance of each layer? Here we simply take out the 281st group of the weights, which becomes a vector with a total of 512 scalars that each corresponding to the contribution to of each layer in this feature map towards the particular prediction score of the class of in this case tabbycat, right? Oh, by the way, the index of tabbycat is 281 in ImageNet. To be specific, here WKC refers to W1 281, similarly W2 281, and to W512 281. Then we can weight average the feature maps against these tabbycat specific weights to generate the final CAM. Mathematically, the class score for an output class C in the CAM is given by the equation that YC equals summation over K WKC 1 over G summation over I summation over G AIGK, where WKC is the weight of the case feature map for class C, and AIGK denotes the pixel at location of IJ in the case feature map, and IJ represent the width and height of the feature map respectively. And actually here they are both 7, and Z is the total number of pixels in one single layer of the feature map, which is essentially multiplication by I and J. So once we get the CAM, once we get the heat map, we need to resize the heat map by using some sort of bilinear interpolation to the original size, then overlay it onto the top of the original image. So there we go. Now we get this visual explanation of the model on the very specific tabby cat photo. So yeah, this is the overall idea of CAM. To recap, CAM is very helpful in explaining the predictions for a given image. However, it involves some disadvantages given that it requires a particular convolutional neural network architecture. The first one is the need of structural modification that ends up with a linear structure, and also the overhead of learn the weights that help with the final feature map projection. And this can be a very limiting factor, right? The second one is the requirement for the gap layer after the convolutional layers, because it suppresses the expressiveness of the model due to the fact that gap will ultimately shrink the entire feature map to one single scalar, which results in a serious information loss, right? It may be too restrictive for other complex tasks, like, for example, VQA, image captioning, object detection, semantic segmentation, etc., other than the simple classification. And last but not least is that due to this very limited structure, we can only explain the last feature map, which followed by the required gap plus FC, and nothing else. Okay, now let's see how we can address the disadvantages which was done in a follow-up work called GradCAM that published in ICCV of 2017. GradCAM stands for Gradient Weighted CAM. It's very smart on array proposing CAM using existing gradients in a CNN. And the motivation of GradCAM was come up with a CAM-like method that does not restrict the network architectures. Let's see how that works. Here's the overall idea and the architecture diagram. The intuition behind GradCAM is actually quite similar as CAM. We want to leverage the spatial information that preserved through the CNN and to understand which parts of the input image were important to a classification prediction result. And so similar to CAM, GradCAM uses the feature maps produced by the last convolutional layer of a CNN. Here's how it works. There's an input image. We have the convolutional part of the network. Now we take the input and push it through the convs, and we are gonna get a convolutional feature maps here. So at this point, for CAM, we would need to do a gap, right? Global average pooling followed by a FC, fully connected layer, to get the weights. But for GradCAM, we can do anything actually. For example, multiple FC that are commonly being used in classification tasks or any other task-specific head structures. The only requirement is that the layers take over after the feature map, denoted by A here, have to be mathematically differentiable so that we can get the gradient. The reason we usually choose the last conv layer as the target feature map is that we assume in this very last feature map, there are more crucial information and high-level semantic information towards that final classification score. Also, there is a consensus that the deeper the feature map goes, the richer the semantic information it becomes. Since its convolution operations are all the way to here, the spatial information is also preserved. So we can expect the last conv layers to have the best compromise between high-level semantics and detailed spatial information. Now we get the probability score for each of the target for say corgi, puppy, tabby cat, tiger cat, right, etc. Similarly, GradCAM heatmap is also a weighted combination of feature maps against these weights or scores for each of the interested feature map layers. Now we have to somehow calculate the scores that weighting each of the feature map according to the influence that they have in the final output. The difference between CAM and GradCAM is in how the feature maps are weighted to make the final heat map. Remember, in CAM, we combine feature maps using those weights taken from the last fully connected layers of the network. While GradCAM doesn't require a particular architecture to obtain the class discriminative localization map. For example, pick up a target class, say YC or YCAT, which is the prediction of class probability, and GradCAM computes the gradients denoted by A prime here through the back propagation. And in deep learning, when we talk about gradients, it's basically in the context of optimization process of the loss function, and specifically refers to the partial derivative of loss function with respect to weights that helps with minimizing the final loss. However, within the context of GradCAM, it's different. Here, gradient refers to partial derivative of YC, which is the score of class C, with respect to the feature maps. So please be aware of that. And now we are gonna backpropagate and end up with a matrix, actually a tensor that has the same size as the target feature maps. And that one is being plotted in colors here. Now what we can do is a global average pooling on each of these backpropagated gradient layers. We end up with a bunch of scalar. Now we use this as scores to weight all those feature maps by multiplying them to the target feature map, the same way as CAM to fuse all the feature maps and project to a single 2D map. Here, gradients information are used to create those weights. It's based on the assumption that the stronger the partial derivative, the more important and influence the case channel of the final feature map has on YC. However, some recent research has shown that it doesn't really work well when locating multiple objects and suffers from the Venetian gradient problem, which we will discuss later in this video. In a nutshell, the activation channels are weighted with the corresponding gradients that representing the importance. The importance weights AK super C is given by AKC equals 1 by z summation over I summation over j dou yc by dou aijk. Don't worry about the terms in this equation. We will deep dive into the mathematical intuition later. Anyway, we would expect a feature map with a higher score to have more positive gradients summed up the expression. Another deviation from CAM is the output followed by a ReLU, which is used to cut off any non-positive values. The intuition behind using ReLU is that negative values more likely contributes to other classes, which are not supposed to be present in the final saliency map. The final output of GradCAM is a heat map, where the hot part corresponds to a region that has stronger influence towards a particular class C, and the size of the map is same as the size of the convolution feature maps used to compute this gradient. Then, again, the heat map have to be resized or upsampled to map back on the original image to visualize which region was relevant in predicting the class C. If there are 1000 possible output classes for any given image, we can end up with 1000 different GradCAM heat maps, one heat map for each class. So fundamentally, GradCAM is a generalization of CAM. It's a method that doesn't subject to any particular architecture. This paper also proposed a variant of GradCAM, namely guided GradCAM. It's a combination of GradCAM's map and the guided backpropagation attribution. To compute the guided GradCAM value, we are going to perform the Hadamard product of the attribution from GBP with a map from GradCAM. Combining GBP and GradCAM allows us to generate sharp attributions. However, it's worth mentioning that guided backpropagation is currently controversial. In sanity check, someone found this method has nothing to do with the model parameters and suggests to stick to the original GradCAM as it appears to rely on the model weights and also the training examples. Now let's derive the equations to mathematically prove why GradCAM becomes a generalization of CAM. Previously, from CAM, we have learned that YC, which is the class score in the last layer, is given by summation over K, WKC, 1 over Z, summation over I, summation over J, AIJ superscript K, where summation K is representing the K feature maps, where we assume now it has K feature maps. And then we have the weights WK superscript C as we saw in CAM. And we know that C corresponds to the weight for each class, and K corresponds to the weight for each activation map of the target feature map. And 1 by Z summation over I summation over J AIJ superscript K is going to be the global average pooling of each of the K feature maps. Alright, this is what we learned through the linear models we implemented in CAM. Now, here we go. Let's assume that f superscript K is given by the term 1 by Z summation over I summation over J A sub ij superscript K. Substituting this capital Fk in the above equation, then we have Yc is going to be summation over K WKC into Fk. Now, took the gradient of Yc with respect to Fk. We have dou Yc by dou Fk is equal to dou Yc with respect to dou Aijk divided by dou Fk with respect to dou Aijk. If we look at this closely, dou Yc by dou Fk, we can find from above equation again which Yc is equal to summation Wck into Fk. According to product rule for derivatives, dou Yc by dou Fk will be Wkc for a particular k, whichever Fk, the global average scalar, remember, from a particular feature map. Now let's take a look at the denominator on the right side of the equation. By the definition of fk, it will turn out to be 1 by z. Since 1 by z is in the denominator, to write the new equation more clearly, we get an into z on the numerator here. If we sum the terms on both sides over I and j, which are all the pixel locations in each feature map, we got the new equation here. Now the summation over height and width denoted by I and j for WCK is just going to be z, which is the total number of pixels in each feature map. And similarly, the constant z comes in front here, followed by summation over I, summation over j, dou yc by dou aijk. Now we can say WCK is given by summation over I, summation over j, dou yc by dou aijk. This equation tells us something fantastic, isn't it? The WCK we learned in the CAM model are simply the summation of the gradients of each of the class score with respect to every pixel in the feature map and adding them all up, which means the class feature weights here are the gradients themselves. And in fact, we don't need the global average pooling and fully connection layers in the end of the model anymore, and we don't need the retraining as the way we did in CAM. The weights can be simply obtained as gradients of the last class score with respect to any feature map where we want to compute the saliency maps. Now we are going to have a normalization factor 1 by z because we've summed over all pixel locations previously, and now we want to divide it across all of the pixels. So this becomes the new weight, and according to the general practice, we denote the partial derivative of yc with regard to aijk as a prime. Eventually, we got to the final saliency map, which given by summation over k, wkc ak, where ak is the different choosing of k's activation map. Because we want to retain only the positive correlations to be shown on the final saliency map, so we apply a ReLU on the weighted combination of the feature maps. Essentially, GradCAM just uses the global average of the gradient flowing into the feature maps of the last convolutional layer. Now, I will give you a demo, and in this demo, we're gonna take VGG19 as example to explain how to implement GradCAM in PyTorch. So, after importing all the required libs, let's start with some helper functions. Initially, we load ImageNet classes from internet into a list, namely classes, because we are going to use pre-trained ImageNet weights. Then let's define 3 image processing helpers that help with loading, pre-processing, and transform, as well as adding a new batch axis by unsqueeze the tensor. Let's try to load in an image using the helper. That's it. Later on, we will push this African elephant photo into the GradCAM explainer. Here, this is the overall architecture diagram of the VGG network. We want to find the result of the last convolutional layer as the target feature map that we are interested in to generate the CAM. So here's the layer. We will load the model from Torch Vision Model Zoo directly, as well as the pre-trained weights, which are trained on ImageNet 1000 classification dataset. We can easily observe the VGG19 layers by printing the model. In this particular implementation of VGG19, the model is divided into 3 major parts, namely features, average pooling, and classifier. Compared with the architecture diagram above, apparently the output of the 35th ReLU layer is exactly the one that we are interested in. Next up, let's modify the model a little bit to make it more suitable with GradCAM method. Once we localize the target feature map, we're going to break the model apart from this crack. That's how the light gets in. By this line of code, we inject an inspection point here. Now we have the capability to pull the gradients and also the activation maps out of the back propagation flow. All the layers prior to this crack are defined as features conv, and all the subsequent layers are continue finished as max pooling plus classifier. And one more thing to notice here is that this adaptive average pooling layer in the original VGG implementation is supposed to allow the system to be used with any arbitrary input sizes. It has no effect in our case because input images have the size of 224 by 224, and consequently, the output of this conv layer followed by a ReLU is a tensor with the shape of 7 by 7. So it won't change anything, right? To reduce the unnecessary computation, let's just remove it from the network. We know that we can compute the gradients in PyTorch by calling the backward method on one tensor. However, PyTorch only catches the gradients of the leaf nodes in the computational graph, such as weights, bias, and other parameters. The gradients of the output with respect to the activation's intermediate values will be discarded as soon as the gradient propagates through them on the way back. Then how to reserve the gradients and pull them out? Here comes the tricky part. There is a callback instrument in PyTorch, namely hooks. Hooks can be used in different scenarios. This link of another notebook I prepared previously will tell how it works in all the different scenarios. I will leave the link down below in the description. You can check it out later if interested. Essentially, the point is we need to attach a hook to this intermediate activation map to pull the corresponding gradients out of the model before they are discarded, as well as the activation map. By this line in the forward function, this is exactly how it works. Here we register the backward hook to the target activation map layer with a callback function, namely activation hook. And in this callback, we can preserve the gradients into a self-variable, namely gradients. Then we can access the variable with across the class, which is to say, we can get gradients and activation maps through these two functions defined below. Now, after the model structure modification, we define an inference function that print out top 3 classes being predicted by the model. Now we come to the GradCAM acquisition function, where we input the gradients and get the output of the final cam. Let's check the code against the figure side by side. I tagged each line in the code with a number and marked it in the figure accordingly. So 7 lines of code corresponds to 7 steps. Firstly, we call the backward function on a particular class score predicted by the model, which is in this case the one referring to the African elephant class, to trigger the back propagate. And since we have hooked up a callback to preserve the gradients with respect to this activation map denoted by A, now we can fetch gradients and activation maps respectively by step 2 and step 3. In the next step, we pull the gradients map simply by a min function. Then come to the weighted average part, where each layer of this activation map will be multiplied by the gradients scalar that representing the importance corresponding to each of the layers, followed by a min function that reduces the dimension and project the result to 2D heat map. In the 6th step, we simply perform a max function to achieve an equivalent of ReLU. Then, we normalize the heat map with a magnitude of 1 by dividing the max value among the entire map. Next up, we define a visualization function called overlayCAM, which uses OpenCV for resizing, scaling, and also color mapping, and then overlays the heat map onto the top of the original image. Finally, we come to the explain section, starting by instantiate the modified VGG model. Then we load the image that had been shown above and take it into the model to perform the forward inference. Let's take a look at the top 3 prediction result out of the model. This pre-trained model is trained out of the ImageNet 1000 classification dataset, so It only covers the 1000 categories that we frequently see in our daily life. It's not a dedicated elephant species classification model. And from the top 3 prediction result, we found that it can not only distinguish this is an elephant, but also distinguish different subspecies. I found 3 pictures online depicting the 3 subspecies in the prediction result, one by one: African elephant, Tusker, and Indian elephant. Let's take a closer look at how the model does it from a CAM perspective. Apparently, the model pays more attention onto the ears, face, skin, and upper part of front leg. Now, let's inspect another image with multiple African elephants. Same as the previous one, we start with the forward inference, followed by CAM acquisition and overlay. Similarly, for this elephant on the right side, the model mainly focuses on the head and ears. For the other one on the left, the wrinkled skin also attracts some attention from the model. In order to verify whether the focus of the model is in the right place, I did some research online and found this article about difference between Indian and the African elephant. However, the top few criteria doesn't help because we can't really tell habitat, diet, and weight from the photos, right? Neither the model. Then came to the next few judgment factors like ears, head shape, and skin. Actually, the skin wrinkleness, which are highly consistent with the focus of the model. It seems that the explanation heat map is making sense. However, when we look closely to this sample image, I found this approach has some shortcomings as it fails to properly localize other elephants other than the 3 in the front. Unfortunately, it has been proven that it does have some limitations when there were multiple instances of objects or when there were occlusions in the image. So here is another image with multiple dogs, and you can see that GradCAM gives such an output where it doesn't seem to capture all the dogs in the image. How can we address this issue? This was done in a work called GradCAM++. The main motivation of GradCAM++ is observing that GradCAM took the gradients of the OYC with respect to each of the pixels in the activation maps, then average all of them to get the final weight. It's evaluating each pixel equally by taking the average when it gets the score scalar. While GradCAM++ states that some pixels contribute more towards a class should get more weight than have equal distribution while computing this weight WKC. Before we go deeper, let's try to understand the intuition of GradCAM++ visually. So here you notice that if we had an image with 3 different objects, say dogs, one on the left occupying a large spatial space, another one on the top right occupying a mid-level space, and another one on the bottom right occupying a smaller space. Let's assume that different feature maps capture different dogs. So for each feature map, let's assume captures each of these objects. And you can see here that in GradCAM, when the saliency map gradients are computed, we can see that the area with the largest space ends up getting most of the gradient, while the gradient towards the rest of the pixels are smaller because they have fewer pixels and hence contribute less towards the output. Well, GradCAM++ tries to overcome this by doing the pixel-wise weighting. Mathematically, GradCAM++ suggested that while computing the final weight, WKC, we are going to give each pixel in each activation map a certain weight as to how they contribute to that saliency map, denoted by alpha sub ij superscript kc. So sub ij corresponds to each ij location of a feature map. K corresponds to the case feature map. C corresponds to the class which we want to look toward. GradCAM++ also adds a ReLU here to ensure that only positive gradients are considered in the computation of this weight. How do we get those alpha IJKC at each pixel level? This lengthy equation is actually how we get a IJKC. What happens is by reorganizing the gradients and using some arithmetic around the expressions, GradCAM++ shows that alpha IJKC can actually be obtained as a closed form expression for the second and third derivatives of the gradients that we already have. If you are interested, please go ahead and look at the paper for GradCAM++ to understand how this derivation is done. Once this derivation is done, the rest of it stays very similar to GradCAM. In GradCAM++, we still do a ReLU at the end of the summation over k, WCK, AK, where WCK is given by summation over I, summation over j, alpha IJKC, ReLU of dou YC by dou AI JK. How does this help? See that given the same image of multiple dogs, GradCAM didn't localize all of them effectively, while GradCAM++ seems to get a better saliency map around the dogs, and it works better when there are 3 dogs. And also it captures the instances when there are structures such as beak or legs under occlusion as compared to GradCAM. Here are more examples of GradCAM++ for multiple occurrences of objects, improved performance over GradCAM. Although GradCAM++ improves some GradCAM deficiencies, it still cannot avoid some problems introduced by the gradient itself. Firstly, we know that the gradient has always been very unreliable and has a lot of noise. In addition, the feature map channel with a larger gradient doesn't necessarily contribute bigger to the class prediction score. During the forward pass, the activation value also need to be considered. Lastly, there are some non-derivable operators in many network head structures where we cannot calculate those gradients through the back propagation. Here, I want to share another grade-free method which overcomes these gradient problems, named as ScoreCAM. In contrast to GradCAM and GradCAM++, which use the gradient information flowing through the last layer of the convolutional neural network to represent the importance of each activation map, ScoreCAM uses the weights of the score obtained for a specific class. Hence, ScoreCAM can get rid of the dependency on the gradient and works as a more general framework, as it only requires access to the class activation map and output score of the model. The pipeline of ScoreCAM is shown in this figure, and it shows all the steps involved to reach the final saliency map. In order to obtain the class discriminative saliency map using ScoreCAM, the process is divided into the following steps. The first step involved is passing images to a CNN model and performing a forward pass. After the forward pass, the activations are extracted from last convolutional layer in the network. Each activation obtained from the last layer, having shape 1 by m by n, is upsampled to the same size as the input image. After upsampling the activation maps, they are normalized with each pixel within the range of 0 to 1 to maintain the relative intensities between the pixels. The normalization is activated using this formula. After the normalization of the activation maps is completed, the highlighted areas of the activation maps are projected on the input space by multiplying each normalized activation map with the original input image to obtain a masked image M with shape 3 by W by H. The masked image M thus obtained are then passed to convolutional neural network with softmax output. After getting the scores for each class, we extract the score of the target class to represent the importance of the case activation map. Then we compute the sum across all the activation maps for the linear combination between the target class score and each activation map. This results in a single activation map, having the same size as that of the input class. Finally, we apply pixel-wise ReLU to the final activation map. We apply ReLU as usual because we are interested only in the features that have a positive influence on the class of interest. So fundamentally, this is how the ScoreCAM works. Alright, that's all for the GradCAM and other CAM variant algorithms we talked today. And at the end of this video, I want to talk about my thoughts on explainable AI and how it can help us. First of all, apparently, it can help the AI models to learn better. When we peek into the black box of AI and obtain a certain explanation, we can inspect whether the decision-making process of the model is biased, and is it fair enough, logical, ethical enough. In this way, we can start to understand the model, improve it, trust it, and even hand over the decision-making authority to AI to achieve the next level automation. The second one I want to talk about is machine teaching. We've seen a major shift coming in the machine learning industry with the transition from machine learning that learn by examples to machine teaching that teach by explanations. Because explainable AI brings out not only the simple result, but also brings its decision-making process, which makes it more plausibly that some professional experience in certain fields could be effectively and widely shared to more people. Let me give an example, which is also a very interesting work, that is teaching human knowledge to identify bird species through AI expert model. Basically, they envisage a scenario where a trained deep learning model functions as a knowledge provider in helping average people like you and me to become better domain experts, like have some capable in distinguishing between different bird species. Briefly, the authors propose a method that obtains useful knowledge from a fine-grained visual classification model that can help to improve novices' ability. The procedure is like first, train a model based on the dataset labeled by domain experts. Then, we can visualize the features learned by the model in the form of attention map to get people to truly learn the knowledge. The author claims that this work could apply to a wide range of end-user applications that require fine-grained recognition outputs. The last one I want to share is about exploring. Many years ago, we had realized that AI has the capability to recognize some new patterns and knowledge that humans have never noticed. We've heard a lot of fancy stories about using AI to conquer tough problems. For example, AI protein folding algorithms solve structures faster than ever, and AlphaGo Zero took just 3 days to master the Chinese board game of Go, purely learned by playing itself millions of times over and over again with no human help. It turns out that AlphaGo discovers better moves that surpass human intelligence on this specific game. However, back then, the AI was considered as narrow because it can only perform one single task at once, such as translating languages or recognize animals. Today, the vision of general AI becomes more promising in the context of the rapid rise of cutting-edge AI technologies, such as large-scale pre-training, multimodality, unsupervised learning, and also the fascinating AIGC. General AI could potentially help humans to explore those unknown worlds and many different tasks. In the next decade, I believe those models like AlphaGo will help alongside humans as scientists and medical experts. And if we bring the models enough explainability, it will help us better advance the frontiers of science and medicine, such as discovering new drugs and materials and solving the mysteries of particle physics. So, these are some of my personal thoughts and reflections. Hopefully, it helps to give a new perspective on the topic of explainable AI. In the next video, we will discuss more about great free algorithms, which make it easier to explain more different models. Alright, stay tuned and see you soon.